In the heart of China, researchers at Southeast University have unveiled a material that feels like it belongs to the future. It looks like cement, it behaves like cement, but it has a secret power hidden within. It cools itself. Unlike conventional materials that trap and radiate heat, this so-called supercool cement reflects nearly all incoming sunlight and radiates its own heat back into the sky. During field tests under blazing midday sun at 101 degrees Fahrenheit, this remarkable cement stayed almost 10 degrees cooler than its surroundings. That's not a small margin, it's a technological leap. Optical measurements showed solar reflectance of over 96% and mid-infrared emissivity at nearly the same level. In simple words, it reflects most of the sunlight away and sends its heat directly into the sky's infrared window. But what makes it unique is not just its cooling performance. Unlike advanced paints or thin films that coat a surface, this cooling effect is built directly into the cement itself. The secret lies in metasurface engineering. As the cement hydrates, it forms reflective crystals of ettringite right at the surface. These crystals scatter sunlight while the bulk structure maintains strong infrared emission. The result is a building material that is both load-bearing and cooling, something competitors have struggled to achieve. Compared to ultra-white cooling paints like those pioneered at Purdue University, which reflect up to 98% of sunlight, this cement may fall just short in raw numbers, but it wins in durability and integration. A paint can fade, weather, or peel. Cement, on the other hand, is the backbone of buildings, pavements, and infrastructure. By embedding the cooling function into the material itself, the researchers have closed one of the biggest gaps in passive radiative cooling technology. To understand why this matters, let's zoom out. Cities worldwide are warming fast, not just from climate change, but also from the urban heat island effect. Pavements, roofs, and walls soak up heat all day, making cooling one of the biggest drains on electricity. Passive daytime radiative cooling, or PDRC, promises a way out by creating surfaces that naturally run cooler than the air without consuming any power. For years, scientists have worked on reflective coatings, photonic films, and nanoparticle paints to reach this goal. But until now, most have been fragile or costly. This breakthrough shows that the cement we already use to build our cities could double as a cooling technology. Imagine entire skylines built with walls and rooftops that cut air conditioning demand, save energy, and reduce greenhouse gases, all without requiring electrical input. And this isn't just theory. The Southeast University team tested their cement under harsh conditions, from UV exposure to freeze-thaw cycles, showing it can endure like any commercial concrete. Of course, challenges remain. Durability must be proven over years in the field. Color options may be limited since ultra-white is not always aesthetically welcomed, and scaling the self-assembling metasurface process to industrial cement production will take time. But if these barriers are overcome, the potential is staggering. Think of what it means strategically. Buildings in hot climates staying cooler with no added energy, roads and pavements that no longer turn into heat traps, solar panels mounted on cool cement bases that run more efficiently, and perhaps most importantly, cities with lower peak electricity demand and reduced reliance on fossil fuels. This new cement is more than a material. It's a vision of how our infrastructure can evolve. It turns one of the most energy-intensive, heat-absorbing substances on Earth into a climate-responsive ally. If paints were the first step, this may be the next chapter, where cooling is designed at the structural level. If you found this deep dive as fascinating as we did, make sure to hit that like button, subscribe to the channel for more future-shaping innovations, and drop a comment below. Do you believe supercool cement could transform our cities?